Last time we got off to a good start on triangularization of a matrix, but we didn't get past the first column. So in this section, we're going to finish the job and complete the algorithm for all columns. It really won't be that much left to do. I just couldn't get it all solved in 15 minutes. So let's go ahead and finish the job now. So here is our matrix, same matrix we had before, same augmented B vector. And this was the result of what we did last time by getting zeros in the first column below the first row, no longer requiring a 1 to be in that position. We're just going to leave row 1 alone altogether. And now we need to get rid of the minus 12 and the 2, and we got to get rid of that 3. That will complete our triangularization. Well, there's really nothing more to change except a slight abstraction to the code we already have. Clearly, we should be able to apply the same code starting at a different pivot cell each time, meaning this pivot cell now is going to move to a minus 4, and just drop the size of the matrix to a 3 by 3. In other words, we're going to only focus on this lower 3 by 3 with its portion of the augmentation until we get that done, and then we'll drop to a 2 by 2, and then we're really done because the last number we can just leave alone. So let's go ahead and complete this, and the way we'll complete it is add yet one more nesting by taking what we had last time and sticking it into yet another for loop. And this time our index is going to be a k index. Now, everything you have from line 2 down to the second last line is exactly what we had at the end of the last time period. But we'd like to generalize this code by marching down the diagonal and stopping one short of the very last row. Well, we already kind of described why. There's nothing to do on the last row. We don't have to eliminate any rows below it. We just leave it alone. The only thing we really need to do is recognize that the inner for loop can no longer start with 2. It's got to start with 1 below whatever the pivot row is. Well, the pivot row initially is going to be 1. K is equal to 1, which means we take for I equals 2 to n. That's exactly what we had on the previous code. If you go back to the last lecture or go back a few slides on the PowerPoint, you'll see that this line said for I equals 2 to n. So numerically, you're going to get the same thing, at least when k is equal to 1. So this multiplier now has to also be located in the right spot because our pivot cell is going to be on the diagonal. So I is now going to be equal to 2, and k is still going to be equal to 1. So on the very first pass through, we're still taking a 2, 1 divided by a 1, 1. That's exactly what we did the very first time we ran that algorithm. But after we go through and compute all this, then the next time through, k is going to be equal to 2, which means I is going to be equal to 3, and we're going to be taking the ratio between a 3, 2 and a 2, 2. And that's exactly what you would expect if you were changing the role of this pivot location to be 1 down and 1 to the right. So basically, the only difference we have going on with this code and what we had before is we've added this outer loop, which is marching down the diagonal of the matrix, and we are adjusting the rest of the codes to take advantage of the fact that the k is moving, that pivot location is moving. And this then completes the full triangularization algorithm in very few but efficient steps. And we will then have a matrix that we can do several things with. The first thing we can do with this matrix is check the rank. Now that we've gotten a diagonal matrix, if you recall, when we looked at the definition of the rank, we had to get 1s going down the main diagonal, and then we took the trace. And the trace was simply adding up 1s or 0s depending on what you got there. You were hoping to get all 1s, and therefore you would get a matrix of full rank. So in this case, if you're going to write some code, which later you will get to do, to calculate the rank, you've got to be a little careful not to just add up the main diagonal entries. In other words, don't quite take the trace. Instead of that, you'll need to check to see if this is 0 or non-zero, and add a 1 if it's non-zero, and don't do anything if it's a 0. So it's a little bit different form, not too much more complex, but that's how you would have to do it. Okay, so that isn't quite echelon form, and therefore we're not quite ready to finish this thing off other than to say this would have full rank. But rather than to go on to reduced echelon form, we're going to use something called back substitution, which is a very fast and stable means to get the right answer. And we'll find next time that it's really easy to find out what the last variable is. You can sort of see right away that you can divide this whole thing by -3 and pick off the result, and the last variable is going to be equal to a 1. But we'll formalize that next time. And then by knowing that answer, we're going to daisy chain back through to find each variable along the way and come up with a solution without actually changing that matrix or trying to reduce it any further. So that takes us to the end of section 2.1b, and we will pick it up with more back substitution next time.